Today I'm solving problem 25 from the AMC 10A of 2022, or the last problem. So let R, S, and T be squares that have vertices at lattice points, i.e. point whose coordinates are both integers in the coordinate plane, together with their interiors. The bottom edge of each square is on the x-axis, like this. The left edge of R and the right edge of S are on the y-axis, and R contains 9/4 as many lattice points as does S. The top two vertices of T are in R union S, and T contains 1/4 of the lattice points contained in R union S. The fraction of lattice points in S that are in S union T is 27 times the fraction of lattice points in R that are in R union T. What is the minimum possible value of the edge length of R plus S plus T? Alright, so basically we can just write, we can use substitution here. So we have this side here. So let's just let these S, T, and S. Now, what this R on the side, T, and S mean, so basically we set them to be the amount of lattice points on this edge. So, but the number of, the length is really just, was really the number of lattice points plus 1. So plus 1. So we have to subtract 3 at the end. Let's get into the first ratio. Alright, so the left edge of R and the right edge of S are, R contains 9/4 as many lattice points as does S. Let's just focus on that one. Well, R, 9/4 as many lattice points as S. Well, this side has R amount of lattice points, so the square R has R squared lattice points. So R squared lattice points is 9/4 times as many lattice points as S, so S squared. So we can square root both sides to get R is equal to 3/2 times S. And we'll be needing this for now, but we have to use these equations right here. That's the first thing. Okay, now let's focus on the second one. The fraction, that's not the second one, but the top two vertices of T are in R union S, and T contains 1/4 of the lattice points contained in R union S. So basically we have T squared, that's how much lattice points are in T. This is 1/4 times the amount of lattice points in R and S, which is R squared plus S squared. But now we see that we have a problem. We're overcounting by one side, this side of S. That's similar on both squares. So we have to subtract an S. But wait here. So we have R and S terms, and we have an R squared here. We can just plug this value of R squared back in. So T squared is equal to 1/4 times, this is 9/4 of S squared, plus S squared minus S. Yeah, that's correct, right? So now we can just add things. T squared is 1/4 times, this is 9/4 S squared, but when you put this other S squared in, that's 9 plus 4, basically 13 S squared over 4. But now you subtract this S. When you put it into the over 4, you subtract 4S. So what you have here is we have 16 T squared is equal to 13. I should take out the factor of S here, but you can get S times 13S minus 4. So we have this here. That's not our second equation, but it's kind of close to it here. So basically, we can just do stuff here. Let's see here. What do we notice? Well, S over here, since they're all squares and they have to be integers, S here is divisible by 2. So what we can do here with this 16t squared is s times something. Since it's divisible by 2, that means it's 2 times some integer. So we have to let that some integer, let's just let s be equal to some integer 2 times j. So now from here we get 16t squared is equal to 2j times 26j minus 4. We can divide by 4 here again to get, so you divide by 4, you get 4t squared. That doesn't look so good, but 4t squared. This is j times 13j minus 2. Yeah. So we're back at, well, square quote-unquote 1. We still see that this is a 4, so that means they're all integers, so that means this has to be divisible by 4. So we have to use another substitution. Letting what? J be equal to 2k. So we get 4t squared is 2k times 26k minus 2. Now when you divide by 4, t squared is equal to k times, 13k minus 1. So we have this other equation here where we will need that for later, but we also have a third term to consider. So once we consider the third term and do a little bit of algebra, we can actually find out what the side length of r plus the side length of t plus the side length of s is. It is time to consider our third thing that we were given. The fraction of lattice points in S that are in S union T is 27 times the fraction of lattice points in R that are in R union T. So we have to declare some new variables for this. Let this side be x and this side be y to make this work. Now let's do this. The fraction of lattice points in S that are in S union T. So first of all, we have this rectangle here. This height is still t. So we have xt over s squared. That's the amount of lattice points here, and s squared. So this is equal to 27 times the fraction of lattice points in R. So this is yt over what, r squared? Well, we already can represent this in s terms because r squared is 9/4 s squared. So x times t over s squared. 27 times yt over, I should write divide, but whatever, yt divided by 9/4 s squared. Alright, so this is basically simple algebra. After a few steps, you will most likely get that x is equal to 12. Yeah, x is equal to 12 here. 12, no, not 12, but 12y. So from this, we can leak out the formula for t here. This is side length t, x, and y. So t here is x plus y minus 1 because there's that one point where it's like combining or something, you could say. So t is equal to, well, x is 12y here, so 13y minus 1. So we can really just use some modulo operators to help us actually solve this problem here. This is kind of confusing, but 13 minus 1. T is essentially a negative 13, not negative 13, but negative 1. Negative 1 mod of 13, since it is 1 less than a 13, or multiple of 13 in this case. So we have this. So t squared is equal to 1 mod 13. So we can leak out some more formulas, but I'm out of space, so we'll come back when we have more space. All right, so here we have these modulo equations here, but we see that we can already implement one of these formulas here, equation 2. Well, we get that t squared is equal to k times -1 mod 13. So this means that k is equal to a -1 mod of 13. And we have more to do with k. Also from equation 2, 13, we see that 13 has to be a perfect square if they are all integers. So we have two constraints. Well, k has to be 1 less than a multiple of 13, and k also has to be a square. Well, let's try the first multiple that's less than 13. K is equal to 12. Question mark? Well, when we plug it in, 12 is obviously not a square, so that is wrong. But now we try k is 25. 25 is a perfect square because, and it's also one less than a factor of 13. This works. K is 25. Working backwards. Well, we let j be equal to 2k, so j is equal to 50, and s is 2j, so s is 100. We have already found out one of the values here. S is equal to 100. Now, we know that s is 100. Well, s is 100 is not our answer, but s equals 100. From here, r is 3 halves s, so r is 150. And finally, t squared. Well, k is 25, so 25 times 13 times 25 minus 1. Once you all calculate this out, this is 25 times 3, 24. Well, this is t squared. We want a square, well, we want t. So we have 25 times 3, 24, but now t is equal to, what, 5 times 18, the positive square root, which is 90. So we have three values here, 100, 150, and 90. So I'll write it here. 100, which is s, plus 150, which is r, plus 90, which is t. Well, this gives us, this right here gives us 340, but we have to subtract 3, as I stated in the very beginning, so minus 3 will yield our answer 337. So that is the solution.